All right, so let's get started with our first question. Okay, and as we can see here, my bad. All right, let's go back. Um, we have to match up each box to its corresponding time graph. And let's look at the first one. A coach leaves the station at 10 a.m. and reaches Gloucester Station at 11:30. So 1.5 hours of motion, and then it stops here for half an hour. It then carries on for 30 minutes and reaches Worcester 40 kilometers later. So immediately we can rule out a couple of them. It cannot be 5, it cannot be 9, and yeah, it cannot be those two because um, they immediately start with returning, right? But we're not returning anywhere, so we can remove 5 and 9. It also cannot be 8 because it cannot be 8 and it cannot be 7 and it cannot be 2 because if you look, right, it carries on. It doesn't return. But in all of these graphs in 7, 8, and 2, they all keep returning back to the same place. So immediately we can cross out those, right? So we know we A cannot be um, 2, 5, 7, 8, or 9, right? So that leaves us 1 and 3 and 4 and 6. Okay, so now let's look at the time specifically because that's where it's going to get a little tricky because they are all similar but slightly different shapes. So it moves to 1.5 hour and it stops um, at after an hour and a half and it stops for 30 minutes. So it's not going to be 1 because you can see it's moving for 2 hours. It could be number 3 because it moves to 1.5 hours and then stops for half an hour. It cannot be 4 because it moves for 2 hours. It cannot be 6 because it only moves for 1 hour, 60 minutes, right? And so immediately we can kind of write our answer anyway because we have eliminated all the others, but let's just see if it's right or not. So it stops for 30 minutes, as you can see, 1.5 to 2, so that's half an hour. And it moves to Worcester for 40 kilometers. You can see when we start moving here, we're at 60. I know it's not very clear, but we're at 60. And then we move up, and it moves to 100. So therefore, number 3 is the answer for that one. Okay? Let's do question F. A motorbike rider rides for 36 miles at a steady speed. She stops to read the map for 15 minutes, then rides for the remaining 24 miles at a very illegal fast speed. Alright, so if you're clever, you're immediately going to look for the graph which has the steepest slope. Okay? And so immediately the ones which I see which are very steep, and none of these repeat, right? So it can only be 4 and 6 because these two have the steepest slopes, right? And so let's look at them. Goes 36 miles at a steady speed, then stops to read the map for 15 minutes, okay? So we want to see a flat line with a slope of 0 for 15 minutes. Do we have that at number 4? You can see 2 hours here and we have 3 hours here. Clearly that's not the one because it stops for half an hour. So it can't be that one. If we look at number 6, stops at 60, resumes at 75, right? So that's a 15-minute stop, and so we know that it's got to be number 6. Let's do another one. Let's look at I. A train is traveling back to Bristol. So immediately, we're going to look at negative slope. After 15 miles, a tree has fallen on the track at Bath and the train stops for 20 minutes while it is cleared. The train then travels the remaining 10 miles slowly. So we want to look at a very gentle gradient towards the end. And this one qualifies, and this one qualifies. The rest don't really, because they want a gentle gradient. Okay, so after 15 miles, a tree is, and also it says traveling back, which means that we want to look at a negative slope. Okay, and let's look at which one travels 15 miles. This one here, it goes from 30 to 12, and it's in kilometers, so it can't be that one. This one 12 to 30, so that's 18, cannot be that one. This one, it's 25 to 10, so it could be that one. And it's also written in miles, not very clear, but it's in miles, and so that looks like the one. And we can see it travels the remaining 10 miles slowly, and so it does travel 10 miles, and it does travel at a relatively not a steep gradient, and so we know that I has to be 5. Okay, so now let's go to the next question. How do you judge if an object is moving slowly or quickly on a distance time graph? Okay, so if you remember anything from the last video, then you'll remember that the slope m is change in y over the change in x, right? And quickly, slowly refers to the speed, right? And this slope can be expressed as the change in distance over the change in time, and that equals speed. And so your answer would be, we can determine whether the object is moving quickly or slowly by determining its slope on a distance time graph. And you can give this math as your reasoning, because m equals the change in y over the change in x, that's the slope, and that's the same as the change in distance over the change in time, which is the speed. And so that would be your answer. Okay? Let's move on to the next question. Look at this distance time graph for a woman walking below. Between 0 and 10 seconds, is the woman accelerating? Yes or no? Well, let's look at this line here. If we want to see if the woman is accelerating, we simply need to see if the line is curving, because if it's a straight line, then that means the speed is constant, right? Which means there's no change in velocity. And so between 0 and 10, we can see there's clearly a straight line, which means that no, the woman is not accelerating. Between 10 and 40 is the woman accelerating. Let's look at it again. Here's 10, here's 40. The line seems to be straight, and so the answer would be no, because the velocity is constant during this time. Is the woman fastest between 0 and 10 or 10 and 40? We want to look at the diagram with the part of the line with the highest slope, right? So as you can see, this, if we continued going on, would go much higher than this curve here. So it's clearly a higher slope. So the woman is traveling fastest between 0 and 10 seconds, right? You can check if you're correct by calculating the gradient of a line. This tells us the speed, right? Which is exactly what we did here. So work out the speed between 0 and 5 seconds by creating a triangle under the line to calculate the gradient. Okay? So, let's look at this one here. At t equals 5 seconds, we're roughly halfway through. And as we can see, it intersects this line at roughly distance of 10. Right? So our change in distance, as we would say, so our slope, right, as speed is change in distance, or the change in time, and that is 10 over 5, and so our velocity is just 2 meters per second. Okay? And again, I really should be writing velocity, because if the line was going downwards, right, like this one, then our answer would be negative. So I think that's my mistake, so I should be more clear on that. So really we mean velocity. Let's move to the next one. This is a word problem. Ben went bushwalking. He started at 8 a.m. and walked 7 kilometers in the first 2 hours. After resting for 30 minutes, he walked another 5 kilometers in the next hour. He spent another hour, and so yada yada yada. And we want to draw a graph to represent Ben's hike. So first, what I'm going to do is I'm going to plot our axes. Okay? Make a line here. Make a line here. Okay? And now we want to, first, we the most important thing we want to make sure we do is we want to label, okay? Otherwise, you're gonna mess this up. So first, this is t, and this is d, distance, this is time, and we want to write our units. So here we're going to write it in hours, because the question has given us the information in hours, so it's just easier to do it in hours. And here is kilometers, that's our unit, right, because the question gives it in kilometers. And so we're going to take 8 a.m. as our starting point, okay? So 8 a.m. is going to be 0 over here, right? First 2 hours, so we're going to have something happening at point 2, and then another in the next hour, so 3, and we want to have our 1 here, and then he walks another 3 hours, so let's have a 4, a 5, and a 6. So our time portion is complete. So seems like he walked quite a bit, 12 kilometers, so we want to, let's say, make this go out all the way to, well, let's just say 12, and let's say here is 6, this is 3, 2, 1, 4, 5, this is 7, this is 8, it's going to be a bit of a squeeze, but I think we'll be fine, and 11. So not the most perfect graph, but you can do better. When you're doing it on paper, you can measure it. So let's start drawing now. He started his walk at, what, 8 a.m. and walked 7 kilometers in the first 2 hours. So he walked 7 kilometers. I'm going to bring this line out all the way out to here, and I'm going to line it up with 2 hours, right? That seems about right. So 7 kilometers in the first 2 hours. That's what it should look like. If you want, you can also draw a little dot to, sort of connect it. Make it very clear for anyone reading it. After resting for 30 minutes, so he rests for 30 minutes, okay? So we want to basically measure roughly, what's going to happen is the distance traveled is going to be 0, right? Because he doesn't walk. And so our line is going to be flat. And what we're going to do is we're going to do half an hour, so roughly halfway between 2 and 3. And that should be about right. And then you can also make, just a reference point showing that it is indeed halfway. So he stops for half an hour, and then he moves another 5 kilometers in the next hour, okay? So we start at 2.5, and we walk another 5 kilometers, so 12, in 1 hour. So it should stop at 3.5. That looks to be roughly halfway. And we can also confirm that by just drawing the line halfway down. Yeah, that's close enough. He spends an hour having lunch before beginning the return of his trip to his starting point. Ooh, so we might have to extend this a bit more here. But let's just see. So he walks, so he rests for 1 hour, so till 4.5 now. Our velocity, our distances traveled is going to be 0. And we can see that here. That's around halfway. And then he returns all the way back to his starting point, and he walks for 3 hours. So we're going to have to put, I think, 7 over here. And he's going to walk for 3 hours, right? So he started at 4.5, and he walks 3 hours. So he's going to stop at 5.5, 6.5, and then 7.5. So let's just extend that a bit more. Make that 8. So he's going to walk till here. And so now what we just do is we make a line connecting that, and just make sure 1, 2, and 3 hours. And so we should be right there. And so if you had to graph that, that is how we would do it. That is the shape. I can't really fit everything in here right now, unfortunately, but that's how it would look like. Apologies. So let's go to our next question. And again, this is the answer from online, and as you can see, we are right. as you can see, the person here used hours, so you might want to keep that in mind. In this particular question, I think that's a bit unfair because they never really asked us to use hours, but that's actually a good thing to keep in mind. You might want to use the time given here, just to be on the safe side. Alright, well, this is a slightly more complicated question now. A car is traveling along a straight horizontal road. The car takes 120 seconds to travel between two sets of traffic lights, which are 2145 meters apart. The car starts from rest at the first set of traffic lights and moves with constant acceleration for 30 seconds until its speed is 22 meters per second. The car remains the speed for t seconds. The car then moves with constant acceleration, coming to rest at the second set of traffic lights. Okay. Let's get right into it. Let's first plot our axes. So I'm going to start with this, make another line. Straight away, we know that our total distance covered is going to be 2145 meters. Okay? Actually, no, we should probably put time first. 120 seconds. We know that the entire occurrence should take roughly 120 seconds. So I'm going to start off with that because that seems like the safest bet. That seems like what we know best so far. So 60, 30, 15. Again, not best scale, but that'll do. 45, 90. Over here we'll have 75. And here we will have 105. Okay, so we're good to go on time now. Again, put your labels. So this is t seconds. Obviously, you're going to make it much nicer looking when you do it yourself. This is velocity. Delete that real quick. V, meters per second. Okay. And finally, let's kind of start sketching. So the car starts from rest at the first set of traffic lights and moves with constant acceleration for 30 seconds until its speed is 22 meters per second. Okay, so let's draw that. Let's make this 30. We'll make this 20. And we'll make this 10. 5. 15, and this can be 25. So the car starts at rest, as you can see, and then moves with constant acceleration for 30 seconds until it reaches 22 meters per second. So what we're going to do is we're going to count to 22. This seems to be around right, and then for 30 seconds. So we want it to stop at 30 seconds. Okay. So that seems about right. Then the car maintains the speed for t seconds. The car then moves with constant deceleration, coming to rest at the second set of traffic lights. Okay, so we do not have enough information to fully answer this one. Okay, and because of that, what I'm just going to assume is I'm going to add a couple more pieces of information. Alright, I'll add another piece of information just to change this up a bit. And what I'll change the question by saying the car travels at constant speed for 45 seconds, coming to rest at uniform deceleration. Okay? And let's just say t is 45 seconds. Then what we'll do is we'll continue this line. As we can see, it's at 30. We'll continue this for 45 seconds. So 30 plus 45 is 75. And because our velocity is constant, right, because we're moving at constant speed, it's going to be a flat line at 22. And so we're going to stop about there, which is 75. And then it comes to rest with constant deceleration at 120 seconds, right, because it comes to rest as a second set of traffic lights, so it is 120. and so that becomes like so. And that's how you would do that question. We made a slight modification because this would involve suvat later. Uh, but yeah, that's how that would look like.